All right, and welcome to Physical Geography. Today we're doing Chapter 4, and for those of you deciding to watch, thank you very much. I put my heart and soul in these things. Just kidding. Let's talk about the atmosphere again. So we've talked already about the atmosphere. We've talked about what it's made of. We've talked about how it reacts with water. And that's kind of giving us this foundation to talk about the next part, which is wind, so that at the end of this section, we'll be able to talk about hurricanes. They all kind of build. So let's talk about how the wind moves. But we'll start off. One of the major effects of wind is desertification. So desertification is where an area of land that is not normally desert is turned into a desert. It can be a natural or a man-made activity, but it's generally man who does this. And what happens is if you have an area that's, say, a grassland, and the land is not managed well, either you overgraze so that the animals eat the grass down to nothing, or maybe you graze too many and then have a drought and the grass dies, you've got bare dirt. Or if you had a forest and you cut the forest down, and now the trees no longer hold the soil in place, and we have all this exposed dirt, and if the wind comes through, right, it whips up the dust, and it blows the dust so that it covers everything with another layer of dust, and that's actually the start of a desert. This is what a dust storm looks like. So these are driven primarily by the wind. All right. So that brings us to the first aspect, wind. First of all, how do we measure it? How do we map it? So what causes wind? We're going to get into this a little bit more detail later on, but wind is just basically caused by uneven heat. As we've talked about, some parts of the Earth's surface get more heat, like the equator, than the poles. And that also drives the process of evaporation and condensation of water, which, as we've talked about, releases energy. So that latent heat, remember when water goes from a liquid to a gas, that extra 540 degrees of energy that's involved, that is actually the fuel that drives hurricanes. So we measure the wind with a tool called an anemometer. And a wind vane measures the direction. And an aerovane is what it is combined. It looks like this. This is an anemometer, that little propeller. The wind blows, it spins. The faster it spins, the faster the wind. This fin catches the wind and it lines up in the direction. So the wind is blowing this way. So this aerovane, right, combines the anemometer and the wind vane, and we know the wind is blowing at, say, 10 miles an hour this way. This is actually a picture of a buoy from Lake Michigan. These solar panels power the whole part. It sends radio data. This is how we measure weather in the middle of Lake Michigan. So how do we rank them? How do we compare them? We use what's called the Beaufort scale. But the Beaufort scale doesn't technically measure the wind. It measures the wind's effect. So if we said that on the Beaufort scale today, the wind is a 1, that means that the wind is between 0 to 5 miles an hour. But the way we know that is examples, like if there was a fire, the smoke goes straight up, right? If we said that it was a gale force wind on the Beaufort scale, that would be a roughly 60 to 65 miles an hour, but it's more about how hard walking is, different aspects. Now we do name the winds. Most of us have probably heard these names and not thought of it, like a northerly wind or the northeasters if you're in the Boston area. And generally speaking, we name winds on the direction they come from. So if you feel the wind in your face, the direction you're looking, that's where it's coming from. If the wind's coming from the west, it's a westerly wind. And we use that in various techniques. So we can talk about wind by compass headings, in relation to water or land, and by prevailing directions. So let's talk about that. Oftentimes an area has a prevailing wind. The wind generally blows the most the same way. In Chicago, generally speaking, weather and wind come from the west. If you've ever watched storms, they usually come from the west. There are exceptions. Last night there was a huge storm that blew through here in Chicago that went from the south to the north, but for the most part to the west. So we call these westerlies. Now, if you've ever been in the tropics, especially if you're on an island in the Caribbean, for instance, you have this pattern called the onshore-offshore wind, and we'll get into that in detail, but during the day, the wind blows from the water to the land. That's an onshore wind. Obviously, it blows from land to the water, offshore wind. So these pictures kind of show you. Here's the onshore wind, the offshore wind. By the way, if this happened in Chicago, we call that a lake breeze. Okay. Sometimes you'll see wind. Very rarely will you hear the wind called by the compass heading, like a 180-degree wind. That's something that can be said, but it's mainly a southerly wind. And then the prevailing wind, this tree is an example. In this area where this tree grows, the wind is generally blowing from the left side of the picture to the right. You can see the tree basically has grown all its branches that way permanently. Like it's permanently being blown in the wind. So how do we show these on a map? Barbs, vectors, and streamlines. Wind barbs were the traditional way until we really had computer graphics. This map shows you what wind barbs look like, and if you zoom in, the barb is this little symbol. It's a line. The line points in the direction the wind's blowing. And at the end of the line, there's a combination of either these little black triangles called flags or these little lines called barbs. And the various combinations will show you the speed. They're measuring here in knots, which is nautical miles per hour. But with computers and animation, you'll see these very often in the news. Wind vectors use just lines with arrows, and they point in the direction the wind's blowing, and these actually they move. The longer the line, the faster the wind. And streamlines just have arrows heads all along these lines. Usually they use color as well, the darker the red to indicate wind speed. So now that we know how we map wind, the next part will be air pressure, because air pressure is the driving force behind wind. So how do we measure that? We use a barometer. For hundreds of years, the mercury barometer was the most common use, but today we use what's called an aneroid barometer, and basically this is a cell, a little mechanical piece that responds to air pressure. Now, air pressure can be thought of in two types, and there's thermal pressure and dynamic pressure. So thermal pressure, we've talked about this, right? If we compress air, it has a higher temperature. So air that is compressed is high pressure. So we see warm air with low pressure because as you warm the air, it expands. And as you cool the air, it contracts. So generally speaking, if you see high pressure, that's cooler air. Now, that can be overridden and it's not constant. So what that means is it's not like air that is 55 degrees is always going to be this air pressure. Air that's 55 degrees will generally be lower pressure than air that is, say, 25 degrees. But that can be changed by dynamic pressure, and that's air movement, the wind, right? If you are standing in the wind and the wind is blowing on you, that is actually increasing your air pressure. Now, when it comes to wind speed and direction, there are three things that control that, especially at the surface of the earth. And the first one is pressure gradient force, and this has everything to do with air pressure. My son's really enjoying his lunch right now. And the other two, the Coriolis force is the rotation of the earth, and friction force. So I'm going to go right here to pressure gradient force. This is changes in pressure across the earth's surface. In other words, if you go to one area that has really high pressure and one area that has low pressure, right, you kind of have a slope in the pressure grid. I'll show you in a map. This is probably one of the most important things because air wants to flow from high pressure to low pressure. In other words, it wants to equalize out. It wants to even out. So if you have really high here and low here, it wants to even out. And the greater the difference between those two areas, the faster the wind will blow. So let's use the example of a bicycle, right? The air around the bicycle is regular density, regular air pressure. But we know that we pump air into the tire at a high pressure to inflate the tire, right? And the rubber of the tire holds that air in place. What happens if you pop the tire, if you put a hole in the tire? What happens? Think about that. All of a sudden you feel that bush of wind coming out. That is the high pressure air trying to equalize out to the low pressure so they're evenly spaced. The same thing, if you blow up a balloon and you blow and blow, right, you're putting more and more air in this confined space. If you pop the balloon, the air rushes out. And that's wind, and that is actually the pressure gradient. So here's what it looks like in a real-world situation. Here we are in this field, right, uniform air pressure. The air pressure is the same all over. There's no pressure gradient, therefore there's no wind. But what if you have high pressure on the left side of the field and lower pressure on the right? The pressure gradient goes from high pressure to low pressure. That's the pressure gradient. That's also the direction wind flows. Air is going to flow from high pressure to low pressure. Now, there is one thing we need to kind of touch on a little bit, and that is we've discussed the fact that air pressure also decreases with elevation. So how come we don't always have wind blowing uphill? Well, we try to equalize that, station pressure. We account for that. Air doesn't always flow uphill too much because of gravity. But the way that meteorologists can map that is we basically just do a little bit of math. And again, don't worry, you're not going to do it. Here's an example. If we have uniform air pressure at sea level, we measure air pressure at 1,013 millibars. But here at 100 meters up, or 300 feet up the hill, it's 1,003 millibars. So that's a difference. So what we do is we just subtract that out, all things being equal, so that this area we know roughly has the same air pressure. And we account for that difference in elevation. So how do we map that? Isobars. So an isobar is a contour line. It's drawn on a map, and every area on that isobar has the same air pressure. So it's a barometric contour line, isobar. Okay? So these are just ways of basically assigning a value on a map to areas high pressure. So here's what it looks like. Here's our little field again. The air pressure here is 1,020 millibars. The air pressure at this little line is 1,016, and this one's 1,012. So we draw that on a map, and that's what that line means. Every point on this line has the same air pressure. Excuse me. But what this also shows us on a map is, now that you know this, and you know that air flows from high to low pressure, when you see these lines, you know that the pressure gradient is going to go from here to here. So any wind that is flowing is going to go that direction. So you can now go look at you can see maps of isobars, and you can see those maps, and that'll show you what the wind pattern is on any given day. The pressure gradient is always going to cross those lines at 90 degrees, right? So let's go back to that image. It's always going to cross them this way. It's never going to go flow next to them, because if there's no difference in pressure, there's nothing to push the wind. Now, just like a topographic map, when the lines are really close, the wind is faster. When the lines are really wide apart, they're much slower. There's a greater difference in pressure. And remember, the greater the difference, the faster the wind. So the bigger or more full the balloon, the faster the wind. All right. Thanks for sticking around and listening to my son sing to us through lunch. He's got a wonderful voice. I'm going to pause right here. Before you go to part 2, please watch the video on the Coriolis force that's in the video lecture section. It'll really make the next part make more sense. So watch that first. And I'll see you in part 2.